Thank you, Katja, for the invitation to give this talk. So I'm going to speak about inverse fractional conductivity problem, and it's kind of like non-local analog of the classical conductivity problem. We have been studying this something like 2 years quite intensively, and finally we have started to publish these different results with my collaborators. Okay, outline of my talk is first to introduce this problem we study. Also, I discuss a little bit about the classical problem, so that also one can see some analogies between the settings. And also, actually, in many of the proofs and properties, we have observed that there is almost always some nice non-local analog of some classical result for the conductivity equation. Then I discuss about more general setting for Calderón, non-local Calderón problems with perturbations. And after that, I go back to this inverse conductivity problem. I discuss about global uniqueness results and how to prove them. And after that, I will introduce counterexamples for this problem if you measure in disjoint sets, and these are general counterexamples. Whenever you measure in disjoint sets, you can always construct counterexamples to this problem. Okay, after that, I will speak about something which is very recent. It's not yet even in ArcSIF, and it's about stability of this problem with full data. Okay, then I finish with giving some open problems. We have been thinking a little bit, but we don't really have that much ideas what to do with these questions. Okay. First, I want to mention my collaborators. So mainly this work is based on my work with Philip Zimmerman, who is PhD candidate at ETH Zurich, and he's going to defend quite soon related to these results. And also some parts are joint work with Giovanni Covi from Heidelberg and Manas Kar from Isar Bhopal, India, and Teemu Tyni from Toronto. Okay, and actually with Giovanni, he has been taking part to 2 of these projects I'm going to discuss today. And my work is actually supported by Finnish Academy of Science and Letters. Okay, the classical conductivity problem, you are all very familiar with it, was, let's say, posed by Calderón in 80s. And it asked if it's possible to determine conductivity gamma from the corresponding boundary measurements, which take the form of voltage and current measurements. So you set some voltage F on the boundary, you measure outcoming flux on the boundary for this potential U, which solves the conductivity equation. And from this data, by changing boundary condition F, you would like to recover this conductivity gamma in the domain. And this is actually a mathematical model for the electrical impedance tomography, which is, let's say, medical imaging method, but there are also other applications. Okay, classical Calderón problem is of course studied really intensively, and there are a lot of recent progress on anisotropic problems, semi-linear problems, and also quasi-linear problems, and so on. But I'm just going to discuss about, let's say, very classical contributions in higher dimensions. So boundary determination result was actually obtained first by Kohn and Vogelius in 84 or 83, and it actually says that if you have smooth boundary, smooth conductivity, then you can determine conductivity and all of its derivatives on the boundary. So in particular, if you assume that your conductivity is real analytic, you can then determine conductivity everywhere. And then actually there was very important contribution by Sylvester and Ullman a couple of years later, where they actually showed that if you have, let's say, see-through conductivity, you can determine that in the interior, and it's not anymore based just on dealing local arguments in the boundary, but you need to really construct some special solutions which you can use to solve the problem. Okay, then there was reconstruction method by Nachman and logarithmic stability by Alessandrini. And then Van Dache showed that actually logarithmic stability is also optimal. And actually about reconstruction method, there is also work by Novikov about the same line as Nachman independently. I should have probably included that as well. Okay, and this problem is studied typically using this Liouville transformation between a conductivity equation and corresponding Schrödinger type equation. Okay, and well, this is of course static Schrödinger equation. And then this potential for the Schrödinger equation is defined by this rule. We are going to see that actually in non-local, let's say non-local analogous problem, there is very similar structures available. Okay, and then how this problem is then solved in the end is to construct special solutions for equations of this type. And they are called CGO solutions, which are kind of like exponentially oscillating solutions, and then there is some error there which converges in suitable sense. And then you take basically high frequencies for these oscillations, and then using, let's say, the original argument, you would actually discover first Fourier transfer of the potential, and then using properties of Fourier transform and this reduction, you can recover this conductivity gamma when it's sufficiently regular. Okay. Then I go for some basic definitions and I move towards this non-local problem. So first I want to define sets which I call bounded in one direction. It's exactly what it is called. So you can take a set which is bounded in one direction. So you choose any direction in Euclidean space, and then somehow if you take slap with that direction, then your set is always subset of something like that. So we call cylindrical domain if we have this product form where we have a bounded set and then rest of the Euclidean space in the product. And then it's called cylindrical domain, and then bounded in one direction if there is a cylindrical domain and some rigid Euclidean motion such that your domain is subset of this type of cylindrical domain. Okay. It's very natural to work on these domains because you can actually show that you have fractional Poincare inequalities or Poincare inequalities for fractional Laplacian in these domains. Okay, then I want to define something I call fractional gradient, and it's defined by this formula. Okay, what it does, it takes two vectors x and y from Rn and gives out a vector in Rn. So it's not exactly like one expects gradient to be, but this is something which is, let's say, related to Cagliardo seminorm in fractional Sobolev spaces when p is equal to 2. Okay, and then by divergence, I denote adjoint operator of this. And actually, fractional gradient it maps from HS to L2, and the adjoint maps from L2 to H minus S. And then if you compose it, divergence and adjoint, you recover a fractional Laplacian. Okay. Now I want to just mention something about Poincare inequality. So if you have domain bounded in one direction, and then let's say P is at least 2, then for any S and T, you can show that there exists some constant independent of the function such that this Poincare inequality holds. And this space is closure of smooth compact supported functions with respect to global HTP norm and smooth compact supported functions in omega. Okay, then actually we have some restriction in this statement when P is between 1 and 2, and we are only able to show it if T is at least 1. Okay, I think it probably holds also when T is less than 1, but I just don't know any proof for it. I know at least 5 different proofs which work in different cases, or maybe even more, but I just don't know anything which would work in this case. Okay, if the set is bounded, then you can get rid of this assumption, and it works nicely. But for these unbounded domains, I don't know any argument. And there is this conjecture, so it's related to how we prove these things. there is certain interpolation argument for Poincaré constants. And what I believe is that if you take any R and Z and any P between 1 and infinity, and you look the optimal Poincaré constant RC of this type, where you have here R, let me say, here Z and here R, and you denote the best possible constant by CRC, then actually the optimal Poincaré constants are equivalent in the sense that they are always related by this relation. Basically, when let's say T is larger than R, then we know that there is inequality to this direction. This one is always smaller or equal to this constant here. But we don't know how to reverse this. But I somehow believe that it should be true. So it's just that if someone knows something about these things, we have been looking hundreds of papers and books and so on. We don't know how to solve these two problems here. But they are not, of course, related to inverse problems that much, but just Bessel potential spaces in fractional Laplacians. Okay, then I move to fractional conductivity equation. So we fix some fractional parameter S between 0 and 1, and then we define the fractional conductivity equation using the fractional gradient and divergence. And then we have some matrix function, which basically takes this form when we write everything in the weak form. So this matrix function here depends on the scalar conductivity gamma, which we assume to be global elliptic. So it's defined actually in whole Euclidean space. And then this bilinear form is also global. Okay, and we say that U solves this equation if for any test function, which is smooth and complex supported omega, this bilinear form here vanishes. And moreover, when you subtract this exterior condition F from U, you get something that is supported in omega, let's say. Okay, so it means that U is equal to F in the exterior in this weak sense. Okay, and what is important is actually this form of bilinear form. And fractional gradient, we don't use that much. It's useful for certain computations to be able to prove results, because if you start with this bilinear form, it's not evident that you can do certain computations. But then using this additional structure that you can actually write this bilinear form also using this operator, you can do some kind of cutoff arguments, for instance. You can place some cutoff here, and then it goes everywhere, and you can get some kind of non-local product rules, for instance, this operator. And just having the bilinear form, bilinear form of this type, it wouldn't be so evident what kind of product rules you have for operators of this kind. Okay. Then I want to define this inverse fractional conductivity problem. So we take omega, which is bounded in one direction, and we then take this restriction on S. This only takes place in dimension 1. And so in dimension 2 and 3 and so on, S is always between 0 and 1. Okay, and then we assume that gamma is elliptic. It's always elliptic in this talk. And then we can define the unique solution to this equation. It exists because of Poincaré inequality and Lax-Milgram theorem. And then denote it by UF. Okay, and then the exterior DR map is defined weakly by just saying that, okay, if we take exterior condition F, we test with G, then it's defined by this bilinear form. Okay. And you can think that this G is, let's say, smooth complex supported function in the exterior. And in particular, because UF is a solution, it does not then depend how you extend it to, let's say, omega. Okay, and then the problem itself asks, if we have that two exterior DR maps agree, does it imply that these conductivities are equal, not only in omega, but everywhere in Rn? Okay. And this is some related geometric illustration. So you can take domain which is bounded in one direction. You can think that it's always bounded by this line and this line over here, and the set omega is there, and then exterior is of course complement. Well, it's interior of the complement, and then you can think, for instance, partial data problems where you set this exterior condition in W1. So that's where you control F, and then you test your data with G, which is supported, let's say, in W2. And then the goal is, by using these, let's say, exterior conditions which somehow generate sources for the problem, and then measuring corresponding exterior Dirichlet-Neumann map here in W2, the goal is to actually recover the conductivity in whole Euclidean space. And this is something new. Like in earlier literature, there are tens of papers. Always coefficients are somehow trivial outside the domain omega where the equation is defined. But in our case, we discovered basically that you can actually recover also information outside the domain. Okay, some comments about approximation properties of these equations. So when S goes to 1, then the fractional conductivity operator converges in the sense of distributions to the classical conductivity operators when it's applied to sufficiently regular functions. Okay, and this is proved in paper of Joan Nicole. Okay, then there is kind of like open problem, or which would be really interesting and important to understand better if there are good approximation properties with respect to the DM maps, and if we can somehow use these approaches to say something about the classical inverse. Okay, and there is actually a related work by Gauss and Ullmann from last year, where they show that if the exterior Cauchy data of fractional powers of elliptic secondary operators agree for S again between 0 and 1, then actually the boundary Cauchy data for classical problems related to this elliptic secondary operator also agree. And also in this work, they actually make simplifying assumption that they know all the coefficients of the equation outside the domain. Okay, and this setting is somehow different than our setting. And of course, it's then interesting, could there be any hope to reverse somehow results of Gauss and Ullmann to again conclude something new about the classical problem using the fractional ones, not the other way around. Okay, then I want to go to these, let's say, abstract non-local Calderón problems. And for that, I'm going to define some basic functional analytic concepts. So I now fix any S, it can be any real number, and then I look bounded bilinear forms in this special potential space, HS. Okay, I say that this B has left unit continuation property on some open non-empty set W if the following holds. You take any function U, and if U vanishes in W, and when you test it from the right-hand side with any smooth complex supported function in W, then U must vanish if the bilinear form always vanishes for these tests. Okay, and then we say that it has the right UCP in the set W if basically the same assumptions hold, but now we have reversed the condition here because we don't assume that the bilinear form is symmetric. Okay, and then finally we want to define what it means for bilinear form to be local. So we say that bilinear form is local if for any two functions which are having disjoint supports, this bilinear form vanishes. Okay, so if the bilinear form is something like generated by L infinity function, which would be just the weighted integral over the whole Rn with respect to this L infinity function, it's an example of local bilinear form. Okay. Then I'm going to set up this Calderón problem in this setting. And then I'm going to state some uniqueness results and approximation results and giving old examples and new examples within this framework. Okay, so we can take again any real number S and then any open set such that the exterior is non-empty. Okay, so it doesn't have to be any more bounded in one direction here. Okay, and then if we have a bounded polynomial from B and we assume that it's coercive in this local space Hs tilde omega, which basically means this, then the following holds. There is unique solutions, there exist solutions and they are unique. And this is just consequence of Lax-Milgram and coercivity. Okay, nothing new basically in that direction. Okay, and then one can also define the abstract ray space and one can define the exterior DM map. And it's defined the exactly same way as earlier. And it's a well-defined bounded linear. Okay, so you can set up the Calderón problem in this abstract functional analytic setting. And then you can actually prove the Runge approximation property. Okay, and this is basically based on the work of Gossalo-Ullman, and then later work of Cecic-Lien and Ruland, and my work with Giovanni Covi and Keijo Mönkkönen. Okay, and basically in this paper by Cecic-Lien and Ruland, they introduced this technique that you can actually also deal with non-symmetric bilinear forms, but in some special case. And then in this work with Philip, we can like push it somehow as general as we thought to be relevant for equations we are interested in. Okay, and so we assume that omega is again just any open set with non-empty exterior. And then we have two bilinear forms L and Q, and we assume that Q is local, and we assume that the sum of these bilinear forms is strongly coercive. Then if L has the right UCP on a non-empty set W, then if you look the solutions by using exterior conditions in W, then actually these solutions to the equation are dense. And then the second property is actually that you can look solutions to the adjoint equation. And if L has left UCP in some non-empty open set W, then solutions to the adjoint equation with exterior conditions in W form a dense set. Okay. So that's kind of like where the non-symmetry shows up. It affects to the fact if you have approximation properties for the solutions of the original equation or of the solutions of the adjoint equation. Okay. And I give here some example where you can apply. This is new example. So you can take any epsilon ball in Rn, and then you can look the complement of the ball, and that's your domain here. Okay, and then you can look actually unique solutions to equation of this type, where now delta is some positive fixed number, and again this bilinear form, a related bilinear form, is actually equivalent to HS norm in whole Rn, so it's coercive by definition. So you get unique solutions to this problem with exterior conditions in this ball B epsilon. And then what follows is actually that solutions to this equation given exterior condition in this small ball, they are dense in this space, which is almost whole Euclidean space. Okay, so somehow heuristically it means that almost all functions in this space are eigenfunctions of fractional Laplace in the same set. Okay, so this is kind of like one possible application. And in domains bounded in one direction, you can take even this parameter delta to 0 because of Poincare inequality. You get unique solutions and coercivity estimate. Okay. Then something I call generalized Gauss-Ullmann theorem, because it's fundamentally based on their ideas that with UCP you can get Runge approximation property. With the Runge approximation property, you can solve non-local inverse problems. So again, we have the same setting as for the Runge approximation. So any open set with non-empty exterior, and we have some bilinear form L, which is kind of like the non-local part of the equation. And if we assume that in W1 L has the right UCP, and in W2 L has the left UCP, and these two sets do not intersect, then for any local bounded bilinear forms Q1 and Q2, we can start to study inverse problem recovering these two bilinear forms in omega. Okay, and then if we assume again, let's say that the forward problem is well posed, and then it means that we can set the define the Dirichlet-Neumann maps, and if these Dirichlet-Neumann maps for these two equations agree, then it means actually that Q1 and Q2 are equal in omega as bilinear forms. Okay, and this is partial data result, so we take exterior condition in W1 and we test in W2. Okay, and this again you need to also consider adjoint equations, and in the end you can show this type of functional analytic result. Okay, then I give some examples when you can solve really non-local Calderón problems for some equations. Okay, in the basic case, it was studied by Gauss, and Ullmann. This W is just L-infinity function in omega, and then the related bilinear form would be of this type. And then this L is just given by fractional Laplacian. Then equations for these operators, you can determine this W uniquely in omega from exterior Dirichlet-Neumann data. And then there is extension where this W is replaced by certain Sobolev multiplier perturbations, which is actually important for our applications. I'm going to speak soon. Okay, then there is another result by Gosselin and Xiao, where they consider the problem where they replace fractional Laplacian by a fractional power of an elliptic second order operator. They can show that it has these UCP properties. They can recover therefore this W. And then there is this paper by Jessic, Lin, and Ruland, where kind of like non-symmetric bilinear forms appear, and they have something which is zeroth order and first order, and they show that you can actually recover this vector field C and also this W uniquely from this data. And then what we did with Kovi, Mönkkönen, and Ullmann was to generalize this result to higher order cases where S can be now anything fractional, which means that anything positive non-integer, and then P can be any, let's say, any local operator, local linear operator, which is having order less than the order of the fractional part. And then we can determine these coefficients A alpha uniquely. They belong to certain spaces of Sobolev multipliers. But there are a lot of examples where this theory applies, and I think you can also, using more general theorems than Lax-Milgrom, something like Lyon's theorem, for instance, you can do similar theory for hyperbolic, parabolic, and many other equations as well. Okay, and then many results in the literature would be probably some special cases of these general functionality results. And also you can do it in manifolds. This same functionality argument we did for function bases in Rn, but you can replace Rn by M, and you can, because it's a functionality argument, you can actually just do it same way. Then you can study operators on a fixed manifold. And if they have these properties, you can study the inverse problems. Okay. Then we have some new examples. So first example is some works on domains without Poincare inequalities. So omega can be anything with non-empty exterior. And then S can be, again, any fractional order. And then you need to just assume that this Q is uniformly positive and bounded. And then you have that this polyomorph related, this is again equivalent with HS norm. So you get coercivity estimate for free, which means that this general functionality theory applies. And you can actually then recover this Q uniquely in omega from this exterior DNT. Okay. Then there are examples where actually this is fractional part and this is now local part. So I take S to be even integer. So it means that this is local operator, this is local operator. I put there something elliptic in between. Okay. And then I add again some Q to make coercivity estimate holds. And again, you can solve this equation. You can show that this equation has unique solutions whenever exterior of omega is non-empty. And this is now an example where you have actually higher order local perturbation to lower order non-local operator, where you can solve the problem. And then something we never wrote anywhere because I didn't think about it at the time was that if you do arbitrarily small fractional perturbation to the classical quantification, this theory applies as well if you measure exterior data. And you can uniquely recover, let's say, this term as a bilinear form, but basically because you can then test with any function in HS omega, you can recover gamma by choosing suitable functions in omega. And you can also plug in anisotropic conductivity here. And you get, which is elliptic. Then you of course get again, if this domain is bounded in one direction, you get that by Poincare inequality, you get the coercivity estimate because this is positive operator of lower order. Okay. And in these cases, in the first case, you have that the solutions to related exterior value problems are dense in HS of omega. In the second one, in HT of omega. And in the third one, you have H1 of omega. That's basically the space where this related bilinear form is bounded. Okay. And there are many other results also on domains bounded in one direction. Okay. Now I move to the fractional inverse conductivity problem. So for that, we define something we call background deviation. So it's denoted by M. And we have this subindex gamma, and it's just square root of gamma minus 1. Okay. And this first theorem is, let's say, generalization of theorem we obtained with Giovanni. And with Giovanni, we had kind of like additional regularity assumptions in the statement. But what we show is that if we take any set which is bounded in one direction, and any S, then if we have uniformly elliptic conductivities and then the background deviations belong to HS n over S, and we make measurements in some set W such that these conductivities are continuous almost everywhere in W. For instance, this is true if we include here epsilon more regularly because of Hölder embeddings. Okay. Then if T and data agree in this W, then conductivities must be equal in whole Rn. So that's our, let's say, main theorem. Okay. And let's say why we consider this setting, for instance, instead, let's say, as we already had this different setting, it was kind of like motivated by this conjecture by Brown that the classical Calderón problem can be solved uniquely for conductivities in W1P when P is larger than N. Okay, and Haberman basically proved this in dimension 3 and 4. And Günther has conjectured in many talks that this is also optimal. So these questions in classical case are open, and we were, let's say, able to show uniqueness. We don't have counter examples if you take something less regular. Okay. Then how to prove something like this? So there are two fundamental properties for these DN maps. Okay. If we assume, okay, well, we take the usual assumptions, we have set which is bounded in one direction, and uniform relative conductivity with these regularity assumptions. And we assume that for two open sets W1 and W2, conductivities agree in these sets where we measure. Then if intersection is non-empty, let me see. Okay, yeah, exactly. So here we have this additional assumption compared to earlier theorem. So we assume that conductivities agree already in the sets where we measure. Then you can show this property and data agree if and only if conductivities are equal everywhere. Okay, and then we need to establish another theorem saying that with this D and data agreeing, we can show that conductivities agree in the set where we measure. And this is something we call exterior determination. Okay, and you combine these two things, you obtain automatically this global uniqueness theorem with partial data. Okay, and this is again the picture of the setting. So there is some intersection W here for these two sets. We set exterior conditions here, we test here, and then in the end we make most of our arguments in this intersection, and that's kind of like geometric picture of this setting. Okay, and how you prove, let's say, this UCP property of the DM maps, which was the first of these two fundamental properties for these DM maps. So first step in the argument is to prove this type of fractional Liouville reduction. So you do basically analogous thing to the classical problem, but you do it with the fractional Laplace for this equation. And this is actually the reason why this fractional conductivity equation is somehow having very nice properties, because it has this analogous reduction to Schrödinger type equation. Okay, and we have so weak regularity assumptions that we have something which is Sobolev multiplier in this space. And actually, to show this identity, you need to really do quite a lot of computation estimates. Okay, and you need to kind of like manipulate the singular integrals and do peak star approximations for conductivities, and then you need to also use some composition estimates for Bessel potentials, and also multiplication estimates for Bessel potentials. And in the end, you can make all these approximation arguments work, and you can show this identity, but it's quite a lot of work. Okay, but when you have it, then you are kind of like good to go, and you can really try to solve the problem, because there is so much nice literature about this fractional Calderón problem for the Schrödinger test. Okay, and then the second step is that, okay, if conductivities agree in the set where we measure, and D and data agree, then we get the same property for the corresponding Schrödinger problems, where we have this kind of like singular potential for the problem. And then it was actually proved by Ruland and Salo using the arguments from this earlier paper by Kossalo and Ullman, that for singular potentials of this kind, if D and data agree, you can recover Q1 and Q2 in Omen. Okay, so that's the third step in the argument. Okay, and then we need to do exterior determination for the fractional Schrödinger equation, which says that, okay, if D and data agree in in W1, when we test in W2, and this intersection is non-empty, then also these potentials, they agree in W. So I didn't emphasize it maybe too much, but this is actually something which is defined in whole Euclidean space. Okay. And it's because bilinear form related, this equation is also defined in whole Euclidean space. Okay. And this uses the earlier interior determination step that actually this Q1 and Q2, they already agreed in order. Okay, and then you can use this data and then some quite simple tricks, and you can find this information as well. Okay, then we are already almost there. So we have that by assumption in this theorem, we assume that conductivities agree in W1 and W2, so they agree in the intersection. Okay, and then we had that, okay, these two perturbations in Schrödinger case, they also must agree, and they were actually defined by this rule. So this is basically how it's defined. Now I simplified notation, and I don't anymore care if this is exactly well defined, but in weak sense it makes sense. Okay, and it basically means that fractional Laplacians of these two functions here and this one, they agree in W because these guys here, they were equal in W already. So fractional Laplacians agree, and also these functions agree themselves in W. Sorry. So we can use this UCP of fractional Laplacians, which says that if fractional Laplacian vanishes and U vanishes in some non-empty open set V, then U is 0 everywhere. And this was proven when P is equal to 2 by Kossala and Ullmann using Caffarelli-Silvestri extension, Karleman estimates of Rugland. And here we need to actually repeat this argument and do it a little bit more carefully to get it for cases where P is larger than 2. So we need to do LP estimates for Caffarelli-Silvestri extensions to really show it, that it holds. And we did it with Manaskar and Philip in another paper, because we wanted to actually study some non-linear P by harmonic equations and their properties, and it was useful there. But then we realized that it actually gives low regularity uniqueness theorems in conductivity equation as well. Okay, and this why we have this was that these functions belong to HS n over S. So we need to have the UCP in that space. And you combine it, you get that, okay, conductivities, they must agree everywhere because these two functions agree everywhere. Okay. Then there is this second step in this proof, which we call exterior determination. And this is quite similar to what you do in classical Calderón problem, but there are of course differences. But what you do, you consider the Dirichlet energy for the equation. And then you notice that, okay, this energy is actually defined by the exterior Dirichlet to Neumann data. And then you construct some special solutions such that this energy somehow concentrates to a point in the exterior where you can fetch the parameters in the equation. Okay, and for that we need to first prove some elliptic estimate. So you take any open set with, let's say, finite measure and positive distance of the domain. You can prove that if you look solutions to this equation, then always L2 of the exterior condition controls HS of the solution in omega. Okay, with some constant independent of F and let's say the solution itself. Okay, and this is somehow good starting point to make this exterior determination argument, because then we can try to find some exterior conditions such that L2 goes to 0, but HS does not. And that's kind of like the idea. Okay, how you can prove it using this quadratic definition of fractional Laplacian. You can prove this elliptic energy estimates. It's quite straightforward how it's done. But with these elliptic estimates, we know what we would like to construct is exterior conditions phi n such that phi n, L2 of phi n goes to 0 as n goes to infinity, but HS actually stays 1. Okay, because then we know that for the corresponding solution in omega vanishes, and the only thing what remains is the contribution from this external condition itself. because of this estimate. Like phi n here, it would go to 0. We get that, okay, HS norm of our solution in omega, when we restrict there, goes also 0. Okay. Then we define these solutions UN, which are unique and given by this external condition phi n. And then because this elliptic energy estimate, these energies for the solution itself and for the external condition, they are like asymptotically equal when n goes to infinity. Okay, and these external conditions are very similar to boundary conditions by Kohn and Vogelius actually. Okay, and then another thing you need to show that, okay, you can choose these external conditions such that this energy concentrates to the value of conductivity at point x0. And that's another part of the proof, but of course, many of the details are quite technical, I'm not showing them. But in the end, you combine these ideas, you can prove the external determination. Okay. Then I'm going to discuss about these counterexamples I mentioned in the beginning. So what we showed that for any non-empty open distance sets W1 and W2, having positive distance to the domain, there always exist two different conductivities which are, let's say, elliptic and smooth, and they have these regularity properties, and D and data agree. So that's kind of like, okay, saying exactly that we have counterexamples. Okay, and compared to the uniqueness result, we didn't have disjoint W1 and W2, but here we have, and this is general counterexample, but we don't know how to do it if W1 or W2, let's say they have limit points on the boundary of omega. Yeah, so that somehow remains open. Our construction does not work there. Okay, and this is kind of like the illustration of the setting. We set external conditions here, and then D and data, when we test it over here, they agree, but then we possibly have something like these background deviations are maybe supported in different sets, for instance, but at least the conductivities are different. Okay, and how to prove it? So using this fractional Liouville reduction, one can actually characterize something we call invariance of data for any disjoint data. And again, we make the usual assumptions, but now there is also this HS assumption. And we assume that conductivities agree in these two sets where the measurements are made, and then we can prove that D and data, partial D and data agree for these two conductivities if and only if the related background deviations satisfy this equation. This is very similar to what you see in classical Calderón problem, but in fractional Calderón problem, this is the way to construct counterexamples, not actually way. Well, with full data, it's also a way to solve the problem, but with partial data, it's a way to construct counterexamples. Okay. And let's assume that this lemma is known. Then how to solve the problem? We do simplifying assumption. We take one of our conductivities to be trivial one, so that our equation here actually would then this Q will just vanish because it's fractional Laplacian of background deviation, but background deviation just vanishes. Okay. So this term here then vanishes, and therefore it just reduces to this type of equation. So we are looking for S harmonic functions in omega, having these regularity assumptions so that our invariance of data applies. And additionally, we need to have positivity condition for the solution here. And then we can construct this counterexample by setting our conductivity to be this one. Okay. And then there is additional restriction where we can set our external conditions, because in our invariance of data, these two conductivities, they must agree in these two sets. Somehow it makes it more harder, at least philosophically, to construct counterexamples. But on the other hand, we don't know how to argue if we don't make the simplifying assumption, because then we don't know how to show something similar to invariance of data. But luckily, even you make constructing counterexamples harder, you can still construct them, and you have somehow a little bit more tools available. But how then solve this equation and get this all these special regularity assumptions? So the idea is to take a slightly larger domain, let's say omega prime, and then find S-harmonic function in this slightly larger domain such that it vanishes near this set. Okay, then you mollify this S-harmonic function in this slightly bigger set. Then if your mollification parameter is small enough, you still have a function which satisfies this equation in smaller set. Okay. Basically because mollification of fractional Laplacian commute. Okay. And then because of mollification, you get all these properties because a priori you know that the solutions in HS exist, and n over s is larger than 2. Well, L infinity is not a problem. You mollify, you get all these regularity properties satisfied, but then you don't yet know if this is true. But for that, you can then scale constructed S-harmonic function to make the solution very small so that you get something like this always satisfied. And it's basically based on linearity of this equation. Okay, there is some geometric picture about this. So here you have on this dark red, you have original domain, then you have here outside this slightly bigger domain, and then you basically make measurements in W1 and W2, and you want that these background deviations or conductivities, they agree in these two sets so that our invariance of data applies. What you do, you generate these exterior conditions for this construction of S-harmonic functions in this set here, and then you can always find solutions to this equation in slightly bigger domains. You mollify, you maybe increase here subforce a little bit, but still you don't touch these two sets, and then you maybe here somehow again increase subforce a little bit, but you keep the function itself S-harmonic here, and even though you increase here subforce a little bit, they still don't touch these two sets where we measure. Okay, that's why we need there some kind of room between W1 and W2 and all. But that's kind of like the idea how you construct these counterexamples. Okay, and then I finally mentioned that there are Lipschitz stability estimates in the exterior. It's based on this uniqueness proof. It's constructive, and you get it somehow directly, and also you can have it with partial data because the argument is local, kind of like similarly as in the classical problem. Okay, then finally something we did recently with Giovanni and Teemu, Tyni, and Philip was to prove logarithmic stability estimates for this problem. So you need to have a priori bound in some, let's say, higher regularity spaces, and then also some L1 bounds in the exterior because of, let's say, L infinity stability in the exterior. So you want to have a priori bound with a dual. And then L1 is kind of like natural. You don't want to maybe work with the dual of L infinity itself. Okay, but then you get logarithmic modulus of continuity, and that with some constant depending on these a priori parameters. Okay, and proof is based on this reduction to Schrödinger case, and then exterior stability estimate, and there is, well, we need stability estimate of Ruland and Salo. And then there is something similar to Alessandrin's work. You can control these Schrödinger data with conductivity data. It's not exactly in this form. There are some powers here and so on, some terms, but it's of this type, let's say. And then there is this type of identity which holds in Rn, which is somehow similar to what Alessandri does. He has some kind of logarithms and boundary conditions and identity of this type, but not exactly this one. And this is kind of like also important in improving these stability estimates. You put everything together, you do 10 pages of estimates, and you get this type of result. Okay. Then I guess I'm out of time, so I don't have time to discuss. But there are, if you take a look of our works and papers, there are several open problems we don't really know how to tackle, and some of them are quite interesting, I think, because this theory is very similar to classical Calderón problem, and somehow that's why and how we found it quite interesting to study this operator. But okay, there are briefly references, so there are actually several works about this. But you can find all of them in arXiv, let's say. Some of them are about to be published and so on, but okay. And with this big picture of my dog playing football in Jyväskylä, I want to thank you for your attention.
Thank you very much, Jesse, for the very nice talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Okay, yes. Could you please go to your open problems? I mean, just take a couple of more minutes. I mean, just to explain some open problems.
Okay. So, well, one of the problems is that we need to assume continuity to be able to do this extra determination at the moment. And I think maybe Brown has slightly better results in classical boundary determination. So that's one of the problems. Can you actually get rid of this continuity assumption in the exterior and still conclude that conductivities must agree in the set where we measure, without making the assumption that conductivities are continuous almost everywhere in W a priori? Okay, that's one problem we don't know how to solve, but I think it could be actually true. Another, which is something quite different, we tried, but we didn't in the end have any good ideas how to do, because we did kind of like higher dimensional version of this classical Calderón problem, but for this non-local operator, how to do something similar to Astala-Päivärinta type theory. We are trying to kind of like find some analogs for Beltrami operators and so on, but we couldn't actually do it. So can you actually work just assuming that you have elliptic L-infinity conductivities? Then you cannot do this Liouville reduction right away. And are there any ways to tackle problem in that? Okay. And then there is this one I already mentioned, that we don't know how to construct these counterexamples because of these multiplication arguments and extensions of domains and so on. And then about stability, we don't know at the moment how to do partial data stability. It's somehow more complicated problem. And then also in this stability estimate, we can like use intensively that smoothness assumption because of work of Ruland and Salo, but also boundedness assumption, and one could actually consider the problem. Can you somehow get rid of unnecessary regularity assumption? And last one, which is kind of like most interesting, maybe at least for me, is if you take some symbol A and you look at equations of this form, can you analyze somehow global uniqueness of this extra value inverse problems in general, and how to generalize this, how to generalize it such way that you can characterize some natural case for these operators. So that's really interesting, and there are works by Goss and Ullman and their collaborators. One work also with Katja on this manifold setting, which is somehow related to have operators of this form. So it's kind of like another way to tackle these problems. And what we do is very specialized at the moment, at least for product type symbols for these operators. But that's really interesting. Understand and have general theory for non-local elliptic inverse problems.
Thank you very much. Thank you very much, Jesse. Very nice problems. Thank you very much. Are there any other questions or comments, please? Please feel free to unmute yourself. Okay, if not, thank you very much, Jesse, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.